Okay, so let's begin. Let's recall the situation. So I have a complex semi-simple Lie algebra L, and I am trying to say something about its structure. In particular, I am trying to somehow create a root system out of it. And this is what we mean by a root system. We are not there yet. We went part of the way, and then I got carried away and I tried to finish everything, and I don't know how good a job I did. So we have to go through it again. Right. So this is the definition. We will visit. This is our goal. Let's recall the general outline of the argument. So you start with a maximal toral subalgebra. A toral subalgebra simply means a Lie algebra which consists of only semi-simple elements. Such things exist because there are semi-simple elements, and moreover, such a Lie subalgebra is always abelian. That was a simple lemma. Okay. And I take a maximal such. Since it consists of commuting semi-simple elements, they will act semi-simply on, first of all, each element will act semi-simply on every representation, in particular the adjoint one. And in fact, we defined semi-simplicity that way, by add semi-simplicity. But the point is that since they all commute with each other, I can simultaneously diagonalize them all. So I write a basis of, if you want, I write a basis of the Lie algebra such that the matrices of add H are all diagonal. And I use that basis to decompose it as direct sum of eigenspaces. Okay. So there is definitely going to be a 0 eigenspace, because all elements of H on itself will act by 0 because they commute. The first fact is that in fact the 0 eigenspace is no bigger, that any element which commutes with all of capital H itself must be in H. Okay. So the proof of this you can read from the book. It has to, as it has to, it does use Jordan decomposition. So the 0 eigenspace is H itself, and every other eigenspace will have non-zero eigenvalues for at least some operators. Okay. Now if I pick one particular eigenvector V, I am sorry if I am repeating this, but I mean I know I am repeating this and I have lost count, but I think it is still worth repeating. If there is a common eigenvector V, what will be the eigenvalue of H on V? It will be some scalar, right? Some scalar times V, but it has to work for every single H. So the eigenvalue will be a function of these H's, and because the action is linear, it will be a linear function, right? So alpha of H times V, where alpha is a linear function of H, in other words, it is in H star. So I see all the linear functions that do occur, and there must be only a finitely many of them, because the whole Lie algebra is finite dimensional. So I get this. This is a direct sum just on the familiar, I mean this is just a familiar thing, that if you have eigenvectors of distinct eigenvalues, they are linearly independent. The same thing works over here. And you saw yet another instance of this when Anupam proved that that any module must be a direct sum of weight submodule. That was the same thing, right? Okay. So so if I have an if I have a function alpha that occurs, then I gather all the vectors on which capital H acts according to that rule, and that is what I call L alpha. Okay. So this is our decomposition, and now I have a very nice combinatorial situation, which is that I have a finite set of vectors in a vector space, which is coming from a semi-simple Lie algebra. So it will have a lot of additional structure. Root system is a way of encapsulating what that structure is. Okay. So now I have to take this finite set and show that it satisfies all of these things. Okay. So we started analyzing which roots came in and what properties they satisfied, etc. Okay. So So let us go through these properties.
Sorry, so actual alphas that occur
Huh.
depend on the basis which diagonalizes H?
No, the alphas that occur, I mean at this moment they seem to depend on the choice of H. Once H comes, then whatever diagonal, I mean its action is diagonal and the eigenvalues are determined. Okay. So, that is one choice that we have made. Later on we will see that this choice does not really matter. Okay, so then let's go through the reasoning that we had yesterday. If I take the bracket of something in L alpha and something in L beta, then that will itself be an eigenvector and the eigenvalues will be governed by this linear function. You recall this was a simple calculation just using Jacobi identity, nothing else. Okay. This was a straightforward fact simply because if you start bracketing by any x in L alpha, then your weight space will keep moving. You will first add alpha, then 2 alpha, then 3 alpha, and all of these are distinct, right? Because remember, this is in a complex vector space. So, you will get infinitely many distinct vectors, they are all linearly independent. So, eventually the weight space itself must die, and so therefore, these operators are nilpotent. Okay. This was a very useful thing, and the way it came about that the killing form, if you take two different weight spaces and unless beta equals minus alpha, the killing form makes both of them orthogonal. This was a consequence of what? Sorry? Is nilpotent, correct? So, and what this allowed us to see is that this kind of thing allowed us to see several things. First of all, I could deduce that the killing form on H itself is non-degenerate, because if it were not, then whatever was in the radical of this would be in the radical for everything else automatically, right. So, this was non-degenerate. So, several things came out of this. First, let us recall what happened to H. Since the killing form here is non-degenerate, therefore, I could use that to identify H and H dual, and therefore, all these special functions that I got, the finitely many, each one of those gave a special vector in here, T alpha. And what is the recipe by which these two are identified? So, what does this mean? Is that is the identification, correct. So, let us keep that in mind. Then, and this non-degeneracy directly gave us this, that phi spans H star. There was one extra bit involved here, right? What was that? Somehow, if it did not, then I started getting a center. So, this eludes me at the moment, but let us not try to go through every single thing. And so, I already have this phi spanning H star. So, which is sort of like that set spanning the vector space, except there is one problem here. The ambient vector space of a root system is supposed to be a real vector space, right. Here I have a complex vector space. So, I have to deal with this issue at some point. Okay. Then the same thing also resulted in that, and more in fact, because if minus alpha were not a root, then everything in here would be in the radical of the killing form by virtue of this. And not only that, it gave us something else. Okay, so this was a calculation, and the same fact, the radical not being 0, also gave us that if the bracket were always 0, then this guy would always have to be 0 for x in C alpha. Okay. So, this showed that the bracket of L alpha, something in L alpha and something in L minus alpha cannot be identically 0. Okay. Then this was an exclamation mark here. The fact that alpha of T alpha is non-zero, this is what told me that if I take something in L alpha, if I take something in L minus alpha, and something in their bracket, then it actually gives me a copy of SL2. So this was the copy that I got here, and the way to correctly choose them, x alpha, y alpha and h alpha. So these equations are just there to ensure that they satisfy, these settings are just there to ensure that they satisfy the same equations as our familiar x, y and h. Okay. So this is where we were. So let's now analyze these representations of S alpha. So what is this? If I take, let's look at this one first. If I take any particular weight space L beta and see how S alpha acts on it, then to make a representation out of it, I have to include everything that could potentially come based on the information that I have at this moment. So H alpha will of course keep this stable by virtue of the, because just because it's an eigenvector, but X alpha will move it to L of alpha plus beta, and Y alpha will move this to L of beta minus alpha, and then I keep acting by them again and again, and I will go to all of these weight spaces. So certainly if I include all of them, then this is going to be stable, because every time I act by X alpha, it just adds one more alpha, and similarly for Y alpha I subtract one more alpha. So this is stable. Okay. And if I take beta to be alpha itself, then I get all multiples of alpha by this procedure. But in order to derive some useful properties, I take not just all integral multiples of alpha, but all conceivable multiples of alpha. Remember, alpha are just some complex valued functions. I can scale such a function by any complex scalar and it will still be in H star. Right now this phi is only a subset of H star, nothing else. It's finite, that's all that we know, and it is closed under minus, that also we proved. Okay. Right. So let's look at these and see what we get. The analysis of this first one has many small steps and they really combine beautifully. Okay. So please pay close attention to this. Right. So let's write down. Sorry, what? Correct. Yeah. Thank you. C. Because otherwise there will be no 0. Yeah, absolutely. Thank you. When C is 0 is when I will get H. Okay. So H is part of this. So in fact, let's do that. Let's do this explicitly. So that C in C star L C alpha plus H. Okay, so let's look at M. And what's the first observation? Weight of H alpha on L C alpha. What is that? That just means the eigenvalue. That is when I take H alpha and take some x in here, it will be a multiple of x. Which multiple? Twice C. Is that clear? Because alpha or rather, okay, let's just write down. I have to take the weight as a function and I have to apply it to the element, right? H alpha. Now H alpha was chosen in such a way that alpha of H alpha is 2. So this is 2C. Okay. Notice, look here. This is the formula for H alpha, right? So when I take alpha of this, I get a scalar multiple of T alpha and I take alpha of that. So I take alpha of T alpha, which by definition is By definition of T alpha, it is this. Okay. So this is 2 because I made it so. But what do I know now? Therefore, this must be an integer. Now I am bringing in what I know from representation theory of SL2. Therefore, twice C is in Z, and I will go and do something here, that after all this, it's not Z mod 2Z, it is Z divided by 2. Or maybe this is a bad way of writing. Perhaps I should write this as half Z. That's a better thing. Not that the other thing is wrong, but sometimes people are lazy and they write Z mod 2, whereas it should be Z mod 2Z always. So 2 times C is in Z. Now we do something even more interesting. So the things that could occur here are half, 1, 3 by 2, 2, so on, and their negatives, correct? Look at now, M is M even, direct sum M odd. What does that mean? M is completely reducible. So I take those representations where all the weights are those irreducible constituents, all of whose weights are even, and those irreducible constituents, all of whose weights are odd in this part. Is this all right? So here I take modules of the type where the weight is 4, 2, 0, minus 2, minus 4, like that. Okay. What I am going to show is that there is nothing here, and what I am going to show is that here there are lots of copies of the trivial representation and a single copy of the adjoint representation, and that is all. Okay. So, claim that this equals trivial representation to, okay, let us write this down here, dimension of H. This is often denoted by L, the rank. So, trivial representation to the L minus 1 direct sum S alpha. And this one is 0. So, those are the claims. Are the claims clear? What is it that what it is that I want to prove? So, there is nothing here. Now, certainly S alpha sits in here, correct? Let us just see that. Because S alpha is acting on the whole Lie algebra, and S alpha is part of that. And what are the weights in S alpha? L alpha, which is of this type, and L minus alpha, which is of this type, and it will also include one line in capital H, namely the bracket of those two. Right. In other words, the line spanned by the vector H alpha, or which is the same T alpha, because the line will be the same. Right. So, that is going to be there. That is certainly going to be there, and the rest of H will also be in there, and nothing else. Okay. So, let us see this. Yes, in fact, they are all conjugate to each other by an automorphism of the Lie algebra. And so, whatever you get from any two of them, it is related by an automorphism of Lie algebra. So, that is how we will see that that dependence is not really there. Okay, so, let us look at this. Now, look at anything in the kernel of alpha. So, take Kernel of, by the way, alpha is a function from H to complex numbers, correct? So, something in the kernel of alpha is going to be an element of this maximal dual subalgebra, right? So, let us call it something, let us call it, I do not know, showing my stunning imagination, I will call it small h, okay, or yeah, okay, h, let us call it, no, the T is also taken. Any other good letter? K alpha, K for kernel, good. So, K alpha. You look at this vector, so, and I will just say note C times K alpha is trivial this is the trivial representation. So, in Raghavan's notation, this is V sub 0, think, right? Is that correct? So, this line, so by the way, what is the trivial representation of any Lie algebra? Every element of the Lie algebra acts by 0. This is the analog of the trivial representation of the group, where everything acts by identity, but we are taking the derivative here. Derivative of a constant is 0, right? So, so is that clear? Let us just see. Certainly, H alpha will act on this by 0 because the brackets are all 0 within H. But how will X alpha act on K alpha? Let us just do this small calculation here. X alpha acting on K alpha is minus of K alpha acting on X alpha. And the reason why I am doing this is because I know how elements of H act on X alpha. Namely, it is a multiple of X alpha itself, but the interesting part here is not that, but rather which multiple. It is alpha, still the minus sign, which is going to be immaterial. But I took this K alpha to be in the kernel of alpha. The linear functional alpha vanishes on this K alpha, and so this is 0. By the same token, Y alpha will also kill K alpha, and so the linear span is is stable, and in fact it acts by the whole Lie algebra. S alpha acts by 0. Okay. So, remember the important point that if you have a representation of SL2 which consists of only even weights, then how many irreducible representations are there? Exactly as many as the dimension of the 0 eigenspace. Is that clear? Because each irreducible representation will give precisely one copy, precisely one dimensional subspace of eigenvalue 0 of H. When you list the eigenvalues, they just are symmetric, right, and 0 occurs exactly once. So, if you look at this M even, the number of things that I get in the irreducible, in the decomposition of it can be detected by checking the 0 weight space here. Okay. So, what is the 0 weight space here? Let us look. The 0 weight space here, if I take any LC alpha, then the weight of that is 2 times C. The weight of, the eigenvalue of H alpha acting on that is 2 times C, and I am interested in the case where this is 0. So, the only possibility is when C is 0. So, the only 0 eigenspace that occurs in M is this H and nothing else. The dimension of H is, I have denoted it by L. So, I need to see L different irreducible representations occur in here. I have already obtained L minus 1 of them because kernel of alpha is a codimension 1 subspace. So, these are L minus 1 of them, and then there is S alpha. Since all of these occur, there is no room left for anything else to occur. So, this is done, right? And we are almost there now. So, what are the consequences of this? Consequences of this. Therefore, M, I mean I will just write this down once again. H direct sum L alpha, not even L alpha. What was S alpha? It was the span of X alpha, Y alpha and H alpha, right? Now H alpha I have taken in here. So, a plus C times the chosen X alpha plus C times Y alpha, and that equals that. From this I immediately read off a slew of things. 1, dimension of L alpha is 1, because the entire L alpha is just that, correct? There is nothing else, right? And if alpha and C alpha are roots, then okay, let's be careful here. Let's be careful here. Let's be careful here. Sorry. So there is a lie here. I'm going too fast. There's something that needs to be modified here. I proved only this. So the only thing that I proved is that M even is this. Right now I do not know about M odd. Okay. So in terms of the C, M even means what values of C are there? Remember, those are the eigenvalues are 2 times C. So when I take the even part, that means C's are all integers, correct? So the half integer values, I don't know anything about them as of now, but soon I will. Okay, with C in Z, then what did I deduce? The only values are 1 and the only values of C are 1 and minus 1, because there is nothing else, right? See, a priori, what was this? This was H plus L alpha plus L minus alpha plus L2 alpha minus L plus L minus 2 alpha plus L3 alpha plus L minus 3 alpha. All of those are included in here, but I saw that there is nothing else. So no integer multiple of alpha is a root. Then let me state this another way. And no integer multiple of alpha except plus or minus 1 is a root. This is a bad sentence, because the exception is not to multiple of alpha, but which multiple? It's a badly constructed sentence, but okay, except plus or minus 1 alpha. Let's make this is a root. But notice now, I want to write this down. Therefore, M even is direct sum of L C alpha, C in Z, and M odd consists of those weight spaces C alpha, where what can I say about C? C is in half integer. How do you write a half integer? Z plus half. But notice, I mean, this is simple and sneaky and nice. What this says in particular is that if alpha is a root, then 2 alpha is not a root. So if alpha is a root, then half alpha cannot be a root also, because if both were roots, then the alpha would be twice of half alpha, right? So applying, see, this applied to an arbitrary root. So what this shows is that if alpha is a root, then 2 alpha, 3 alpha, 4 alpha cannot be roots, and therefore half alpha, 1/3 alpha, 1/4 alpha, they cannot be roots, right? Anyway, the 1/3, 1/4 I don't really care about, because anyway I knew that they could at most be half integers, but I did get from this that half alpha is not a root. and half alpha is not a root. Now I claim that I am done here. Why? Because if there were anything here, let's say V1, V3, V5, whatever, if there were anything here, then the moment you have an odd highest weight irreducible representation of SL2, it would give rise to a eigenvalue 1. Right? If you have V5, then eigenvalues are 5, 3, 1, minus 1, minus 3, minus 5. No matter what, there is the eigenvalue 1 you must see. Where would the eigenvalue 1 come from? It would come from having L of half alpha. But there is no L of half alpha, I just showed that. Therefore, this is also 0. Okay, so we got a lot out of this. So this analysis is done. I can perhaps start writing some things. So I had this written. So this was yet another list now, proposition. I don't know, okay, I will call this now A, B, C, D. Dimension of L alpha is 1. And this I have already written. This is just sort of a B only scalar. I don't think I will write this down because we have said everything and just. So I will just read this out. If alpha is a root, then dimension of L alpha is 1. I have written that. The only scalar multiple of alpha in the root systems are plus or minus alpha. So that is also done. Okay. Now we start. Okay, might as well write down. Here. This is interesting. This needs to be written down. If alpha and beta are in phi, then beta of H alpha is in Z. You should think of it as this one here. So I want to think of H alpha as somehow alpha check. All right. So this is the integrality, and there is also going to be and this I have done. Beta minus beta of H alpha times alpha is in phi. And lastly, if alpha, beta and alpha plus beta are all in phi, then the bracket of L alpha. By the way, what do I know about the bracket of L alpha and L beta? It is contained in L alpha plus beta. What this, by the way, I have to prove these claims. So what I know is that it is contained in L of alpha plus beta. I also know that both of these are, that in fact all three of these, if they are there, they are one dimensional. I proved that already. But nonetheless, it could happen that they commute with each other. So the point is that it does not. Okay. So these things will come, especially these very interesting things. They will come by looking at the other one n. So, let us look at this, and here I can just say various things. Look at n. So, what can you say? So, remember all of this came just by looking at the weights of this guy and knowing how representation theory of SL2 is. So, let us look at the weights here. So, weight of H alpha on L beta plus I alpha is what? Let us write this down. Beta plus I alpha acting on H alpha, correct? Which equals beta of H alpha. I do not know what that is, right? Plus 2I. What do I know about this? This whole thing, this is a weight, right, of a copy of SL2 on a representation of SL2. Therefore, this must be an integer. And so, I subtract 2I and I still get an integer. So, that gives me so let us give it a minute, see if you can think of why the other ones are true and what else I can sort of milk out of this representation. So, this is just about the weights, but what sort of representation is there? See, over here I actually nailed down exactly what representation it must be, certain copies of trivial ones and an S alpha. Can I say something about this representation? What is the dimension of each weight space? 1, because I have already proved that for an arbitrary weight the corresponding weight space is 1 dimensional. I should not say, see, the corresponding root space is 1 dimensional, right? Those phi's are called roots, but here I am thinking of this as a weight space for a single H alpha. Nonetheless, all of these weight spaces in this representation are 1 dimensional. What does that say about the representation? If I have SL2 and if I have a representation in which all weight spaces occur with dimension 1, what does that say? Well, I mean, a little bit more careful. You could have an even one and an odd one, and their direct sum would still, okay. But nonetheless, all the weights over here have the same parity, correct? All the weights have the same parity and all weights are 1 dimensional. Therefore, it must look like an irreducible representation of even of some highest weight, correct. So, therefore, n is irreducible representation of S alpha. All right. So, I have this and I have this. Can you see one of these? This one is now, I claim that this one is clear. Why is that? Okay. See, this is an irreducible representation, right? So, let us write down. So, what does that mean? See, if there is a weight, you look at the extreme weight, right? So, let us look at it this way. The weights increase by 2 every time the index I goes up by 1, correct? So, the largest possible weight that occurs will be will correspond to beta plus some, let me use the same, Q and R is what the book uses. So, some beta plus Q times alpha. So, I will just say root root and the weight of H alpha on that. Let us make a table. So, beta plus Q alpha, I just wrote it and I forgot, beta plus Q alpha, what will be the weight? Beta of H alpha plus 2 times Q. But then what this says is that every single weight from this number to its negative with differences of 2 must occur. But in particular what this means is that if I go 2 less than this, then that weight must occur. But where will that come from? That will come from beta plus Q minus 1 times alpha. There is no other weight can come, right. So, that means that all the roots from here to beta minus R alpha, they must occur, and this one will give beta of H alpha minus 2R. Is that clear? And all of this I will just say unbroken. So, what this says is that the root string, the alpha root string passing through the root beta is unbroken. In other words, it cannot happen that beta minus 3 alpha is a root, beta minus 2 alpha is not a root, and then beta minus alpha is again a root. That cannot happen, just because of how irreducible representations of SL2 look like, correct. So, there are several interesting things that will come out of it, but the first one, is this clear now? Because you look at the root string, if alpha plus beta is a root, then that means that this L alpha plus beta is part of this N, and therefore, when I act by X alpha, which is just like X in SL2, it cannot kill. The vector that is killed will come only after this. So, in other words, when I act by X alpha on this L beta, it must take it to a non-zero vector, but that vector will be in the root space alpha plus beta. So, it cannot vanish. Okay. If it vanished, then that means that X alpha acting on this would be 0, but moreover this one occurs, right. This one does occur as a root, so it must be part of this representation, and the one that is killed by X alpha must be alpha plus beta or something higher. Now, we have explicit formulas, right. So, see those so if you draw various, you will see these diagrams like this written. If so, this will be for which one? V3, no sorry, V4, correct. So, if this is the case, if this is the representation of SL2, all the Hs will act by respective eigenvalues. This will be 4, 2, 0, minus 2, minus 4, and then what will happen? Action of X will take one dot to the next dot, or maybe with some scalar multiple, it depends on how you normalize it. And then this 0, and then Y action moves backwards. All of these come with actual scalar multiples depending on what you use as the basis vector, and that also you can write down, but that's the thing, right. So, what this amounts to showing is that if L alpha plus beta is there, then that means that beta and alpha plus beta, they are two consecutive dots, and X is moving, then X has to move one in a non-zero fashion to the other one, because the only thing that X acts 0 on is the highest one, since alpha plus beta occurs, right. So, the one previous to it cannot kill it. Okay, so this is a very specific thing actually, but the interesting one is this. So, where does this come from? Where does this, see, in all of this you can okay, this real versus complex, we will say something about it, but it's not really a big deal at this moment. But there is one player in all of this which has not made its appearance at all over there. What is that? There is no S alpha, correct? So, what is S alpha? S alpha, remember, if you recall, S alpha was defined by this, but in the context of SL2, what is S alpha? There is a symmetry, right? If you reflect, if you just take minus of a root, it's a root. If the reflection in the origin preserves the weights that occur, that is what is going to give us the thing. So, in particular, what do I get here? That this is an unbroken, if you look at these integers, this is an unbroken string. If you take the corresponding weights of H alpha, I am going to get a list of integers, but those integers must be symmetric around 0. That's what I know from SL2 representation theory, right? So, in particular, this must be minus of that. Those are the extreme weights. Again, maybe I did not say this explicitly. Beta minus R alpha is the leftmost one that occurs, and beta plus Q alpha is the rightmost one that occurs. That's how I am choosing to call R. I mean, that's what I am defining R and Q to be, respectively. So, these two integers must be negatives of each other. Let's write that down and see what it gives me. So, just do this calculation and see what it says. It's going to give me some relation involving Q and R. And what does it say? Beta of H alpha minus 2R is minus of beta of H alpha plus 2Q. What does this give? Beta of H alpha on one side and the 2 cancels out, and I will get R minus Q. So, in fact, we already saw that it's an integer, but which integer is it? Well, it's that integer. Okay. Now, what do you see? Where does the fact that this is also a root, where will that come from? See, here is beta minus R alpha, and here is beta plus Q alpha. Somewhere in this string, beta occurs. That's how I started, correct? So, here is beta. Just as these two are mirror images, what will be the mirror image of this one? That's how it must come, right? Because remember what that is. It is S alpha or beta. It's a reflection of. So, that's how it must come. So, let's just see if we can see it in a minute. This is a matter of beta of H alpha is R minus Q. So, how do you do this calculation? So, let's see. So, let's solve. So, beta plus I alpha such that, so what is the such that beta plus I alpha, how is this going to be? The weight that this is going to give for H alpha is beta of H alpha, correct? Yes, and this is a weight that occurs in N, therefore, minus of that must also occur as a weight. So, beta of plus I alpha such that beta plus I alpha of H alpha is minus of this is also a root. So, what is that I? Just see that. It's going to work out very easily, you see, because alpha of H alpha is 2. So, just see. Or or maybe the relationship, okay, I don't know how easily I didn't work this out. Perhaps we have to use the fact that this is r minus q. Just see this for a moment. That is a string. Oh, okay, so fine. Correct. So, and that is correct. Yes, that is fine. Using what he is saying is that instead of looking at it like this, everything in between must occur. And notice that beta of h alpha is r minus q. So, just notice that it occurs in between. That is correct. That is also a perfectly correct thing. But I would like to see that it is obtained by reflecting beta, because that is what its meaning is, right? Sorry? I mean, that is how it must happen. I did not check it, but that is how it has to work out. So, check this, find this. So, I will leave this dot dot dot, but let's complete the proof that he was giving. So, what he is saying is that this beta of h alpha is r minus q. So, from q alpha you have to subtract alpha q times and then r times in order to get here. So, how many times do you get to subtract alpha to go here? Q plus r times, correct? Whereas here I am subtracting alpha q minus r times, right? It does not matter whether q is bigger than r or small. Well, one second. I am getting confused. Can somebody help me out here? No, see, that is okay. See, the other thing is okay. Now this is okay. So just 1 second. Now I see the very blithely I wrote beta on this side. This picture could be misleading. Beta could be either here or here. It could give rise to a positive or a negative thing. Correct? So, but nonetheless this should work out. Okay. Now, what he was saying will make sense. You just make two cases, and in either case it will work out. Okay. So, you wanted to say something?
So you're saying you now determine I, is it?
I want to see, that's how. I want to determine I, and I want to see that it is actually equal to this. That is what I would like to happen. Direct calculation. Okay, so you realize when I am standing on my feet, I am completely dumb. So you will have to dictate to me. If I put okay, correct. So just tell me. So beta plus, right? Q minus r times alpha. Correct. That is the same thing as that. So let's do that calculation. That is acting on h alpha. Good. So that is beta of h alpha. Wonderful. I mean, you can solve for I and use this fact to get the same thing. Right? You don't need that fact. Just right. So correct. Just using the fact that alpha of h alpha is 2. Right? So whichever way or directly. I equals minus of beta of h alpha. But so nonetheless, I sort of insisted on this because I just wanted to make the point that this S alpha is really just the symmetry of SL2. And since you have many SL2s sitting in, so you get those various symmetries. Okay, so let's take stock and let's see what all things we have proved and whether we are already done or not. So let's see here. Do we have a root system? So, I have a finite set of vectors in a complex vector space. I want it to be in a real vector space. Is there any way to get around it easily? I can just take the real span. So, let us just make this definition. So, now this phi is finally going to connect to that. Until now it was just sitting in the air. So, define V to be the real span of phi. Does everything go through easily? There are some things to say here, I think. So, the fact that 0 is not in there is okay, because it was not there to begin with. That is going to be by definition. Okay. Now, for alpha in phi, I need to define an alpha check. Where is the alpha check? So, I need to define what an alpha check is, and recall what alpha check is. It needs to be now a real okay. So, how do I define alpha check? Alpha check is in the dual of this real vector space. That means I need to take anything in the span of this and assign to it a real number. Okay. Since phi spans R, it is okay if this linear functional is defined only on phi and gives real numbers over there. Okay. As long as I already independently know linearity. See, you cannot arbitrarily assign things to phi, because there may be relations among them. So, perhaps you can take the base and do it, but nonetheless it's all of this is much easier than that. So, alpha check is something that needs to take a root and assign to it a real number. What is it going to be? I already said it. Alpha check is going to be H alpha, right. So, what is this functional going to be? So, again notice this is, remember alpha is sitting in H star. So, alpha check needs to sit in the dual of that. Now, which is H? Again, I have done some messing around with scalars, but it does not really matter. As long as I can take as long as I have a function, as long as I have a linear rule which takes something in phi and produces a real number, I am okay. So, alpha check is going to be equal to H alpha. In what way? I will just say equal to in quotation marks. So, I take any root beta and I produce a real number. Which real number? And I know this will work because it is much better than a real number. It is actually an integer. Okay. So, I am all right here. So, there is alpha check such that this is still valid. It's sort of, I mean, this tells you, right, that alpha check has to be H alpha, and for all beta in phi, this formula is now true. Okay. So, because Vishwanath defined a root system in a more basic or more fundamental way than Humphreys did, our task was easier. I still want to complete this using Humphreys, because there are some interesting things to say here. And if you do not want to follow this, maybe I will just make one comment. Was it necessary? If I wanted to make a vector space, then what sort of coefficients did I need to put in here? I did not really need to go to R. I could have just worked with Q, right? Z, not Z because I need a field, but Q would still be enough because all these things already lived in Q. So, let us just say this in a somewhat different way. The reason why I am doing this is because Humphreys, for him a root system is something that comes along with, it sits not just in a real vector space, but in a Euclidean space. So, you have to have a non-degenerate positive definite bilinear form. Okay. So, how do you get this form? Well, what is this form going to be? It is going to be the killing form, but I have to see positive definiteness, and for that I have to come to real numbers because there is no sense otherwise over a complex vector space. So, there are some noises to make, and I will do that and then I will stop. Okay, I mean, I'll just. There is one neat calculation which I wanted to show you, but okay, fine. So, I will just say how to get Euclidean, I mean, so with the positive definite bilinear form. And so, the calculation that he says makes is the following, that if you take a basis alpha 1 up to alpha L of H star consisting of, I will be a little quick here because consisting of roots. This is always possible because it spans, right. So, let us write down a little calculation here. So, if I take any beta root, I can write it as sigma Ci alpha I going from 1 to L, where these C's are alpha I, sorry, where what are C's? Yeah, but actually I want to say that they are rationals. So, where is this going to come from? So, where will rationality have to be derived from? It will have to be derived from, I mean, there is only one place where something or the other is, there is only one place where I can get a handle on something being rational, that is only on integrality, right. So, I have to somehow get this. Now, what is this? I can get this in terms of the form. So, let's write this down here somewhere. So, form on H star. So, what is the form on H star? It is if I take any lambda and mu, I will write this because this is what Vishwanath had. So, what is this by definition? See, currently the form does not live on H star, it lives on H, but it is okay, no? Then I can. So, this by definition is the killing form of its partners, right. So, the one that corresponds to lambda, I called it T lambda, T mu. Remember, this didn't depend on lambda being a root, it was just an identification of a vector space with its dual. So, you can do this beta alpha j equals sigma, I will write Ci on this side now, alpha I alpha j, I going from 1 to n. What do I know about these things? These are not known to be integers. What is known to be integers is beta of H alpha. So, what is beta of H alpha? Let us write this down. Beta of H alpha is T beta H alpha, but I want to write everything in terms of the alpha and beta now. So, this is going to be 2. So, this H alpha gives me the killing form of T alpha with itself, which is really alpha alpha beta alpha. These are integers, right. So, somehow or the other I want to get this equation in terms of this. Let me not write down the whole thing, but so I have this. I do not know anything about these as yet, but it is okay. I will just divide this by alpha j alpha j. Remember, j is fixed here, I is the thing that is saying alpha j alpha j. And then you look at this, these are integers, these are integers. So, I write, so let me call this vector as some v. Okay, I will put 2 also. Okay, so 2. But for the purpose that I have in mind, it does not really matter. It's rational. That's all I. That's all I. So this is going to be some matrix. Now as you vary over, so some matrix times this vector of c's. The point is, I know this and I know this, and this matrix is invertible because the form is non-degenerate, and so therefore this C is explicitly equal to M inverse times V, and so the coefficients are all rational numbers if you want. The reason why I wanted to do this rather than just that cop out is because there is a nice calculation of how the Killing form works on the Lie algebra H in terms of the root space decomposition. Let us write that down. See, so far all that it gives me is that every root is a rational linear combination of the simple roots, but I still want to see that these inner products themselves are all rational numbers, and I want to deduce positive definiteness. So, there is a little calculation to do. Let us do that and stop. So, this is the thing. For lambda and mu in H star, what is lambda mu? That is k of T lambda T mu, which is, recall, trace of add T lambda add T mu. What is that? This is an explicit calculation. How do I calculate the trace? I will use this basis. See, if I wanted to calculate this for Lie algebra elements, then it is hard. But if I want to calculate this for elements of H, then it is easy because I know exactly how they act. They do act diagonally. So, the matrices themselves are diagonal. I just have to calculate the entries and add them up, right. So, what is this? So, let us look at, okay. So, I have to see the contribution of each weight space. From here, what will be the contribution? 0. What will be the calculation? There will be one contribution from each alpha, right, and it is one dimensional. So, this will be a sum over alpha in. And how will this act on L alpha? Correct. So, alpha of T mu, but alpha of T mu is the same thing as, okay, I will write down alpha of T mu times alpha of T lambda. That is really the same, the sum of alpha mu and alpha lambda, correct? So, where do we go from here? So, if I take let us say beta in the root system, then what is that? We are almost there, okay. Is this okay? I have just applied this whole thing to lambda equal to mu equal to beta. What do I get from here? I want to get from here two things. One is I want to get that this inner product is also rational. You grant this to me for a moment. It's just a question of messing around a little bit. But if this were a rational thing, then what else? Then what would this equation immediately imply? It's positive definite, right? Correct? because I mean these span, and then you can get everything in terms of this. So, why is it rational? Because see, the reason why this is rational is, again I have to get to integrality. Remember this, what is this thing? This is 2 beta alpha divided by alpha alpha, correct? So, here is the alpha beta term. So, in order to get that denominator, I have to divide this whole thing through by beta beta square, and the terms that you will get on this side will all be rational square terms, etc. So, now I will not write this down in detail, Humphreys has it. So, the conclusion is that you first get that all of these inner products are rational, and therefore, the form is also positive definite. But this calculation is interesting and useful. So,
It's not zero.
what's not 0?
Positive definite. If you take a non-zero vector,
It should be positive also. So, now why can't be okay. So, this is, but everything will be but not everything can be 0, right, because there is alpha alpha also in there, right. Beta is fixed.
Beta of t beta, that is always
Huh.
inner product that we have proved of. Beta of t beta.
Correct, exactly. That is. So, I will just write this down. So, divide by, just to have it, divide by beta beta square and conclude that alpha beta is in Q. And this form is positive definite. Positive definite on what? On the Q vector space spanned by the roots. Okay. So, as far as my understanding goes, I will stick my neck out and say that I do not think that this has anything much more than what we said over there, except perhaps this calculation. I think this is a useful thing. So, I think we should stop here.